Welcome to the course on Introduction to Electrical Engineering. We will have today lecture 17 on the topic of diode based circuits. We like to introduce with the rectification technology, then application, type of rectification, rectification circuit applications again for and clipper and clampers like. So, coming to the introduction to the today topic, this is typically like a history of the rectification. So, early experiment with direct current power relies on leaden jars, rudimentary batteries which had to be charged via manual labor. Then later on DC based lighting were prevalent in the late 1800, and due to the efficiency and safety reason, of course, the alternating current system used for providing the electrical power, which we already discussed what the war of AC and DC. Finally, the AC won the war. So, it has gone to the AC. So, now coming to this, however, connecting DC based system on AC power will damage the said system, and technology was required to do so. So, a means of process to convert AC into DC is required, which called rectification, which we like to cover of course today. So, rectification by definition is in electrical power terminology, it is a conversion of alternating current to the direct current, and fundamental concept is AC reverses current every half cycle. So, DC has a constant current polarity throughout the period, and we have to convert AC into DC, need to maintain constant current direction across the load. So, since there are plenty of the load which can operate more comfortably upon the DC supply, so we have to convert this AC into DC, and you have plenty of load around like which runs really on the DC like. And this rectification technology of course, is started first from electromechanical, typically like which called synchronous rectifier, use the motor attached to the metal contact that switched direction of current flow time with the AC voltage, and people use the motor generator set for the purpose. So, an AC motor driving the DC generator by providing the DC supply to the load, and this has been commercially used for many applications, typically like a wall-nut system where we really use the variable DC supply for controlling the DC motor also in the industry like. So, this was the one of the way, but of course, you have a two machine here, one is of AC motor, another is your DC generator. So, the efficiency of both machines, maintenance requirement, cost, space requirement certainly has been much higher with respect to the the changing technology like. So, we of course, have a static device virtually which have been used for rectification. So, that was first electrolyte, two different material electrodes suspended in electrolyte provide the different resistance depending on the current flow. So, that was the first technology to convert this typically from your AC to DC, and later on people use mercury or rectifier which are used for rectification. So, a sealed vessel with mercury in it provide the DC power by transmitting electricity through the ionized mercury vapor and capable of power of order of hundreds of kilowatt. It was initially used, but of course, it was having certainly losses were more, and you require the gate signal for controlling signal also for that. But of course, it has been used first generation of HVDC transmission like in Europe. Of course, this is typically these are the some of the photographs from steel manufacturing plant of rectification in the Germany, and of course, later on it is gone again for vacuum tube. So, rectification technology of course, gone first typically diode vacuum tube were evolved and used in early 1900 in many applications like radio, television capable of high voltage, but relatively low current, and later on of course, in around mid of you can call it around 1950, we have a technology called solid state devices of low power, as you can see the photograph also here of silicon diode. So, most commonly used are the silicon and germanium diode, widely used for low power application and substantially low forward voltage drop 0.3 volt for germanium when it is conducting and 0.7 volt for silicon diode like. So, this solid state diodes extensively used even later on for high power. And of course, we have a diodes, and then we use other devices also like thyristor used in HVDC for rectification, and of course, finally, nowadays even we are using IGCT insulated gate commuted thyristor which are used for rectification. Of course, we have a many other switches like we call active switches are used in place of diodes nowadays like. We have a many devices like IGBT with the proper configuration we use for this rectification with the concept, but of course, here we like to only introduce the basic simple typically the diode rectifier like So, the diodes provide compact and expensive means of rectification, and these can create rectifiers from multiple diodes, or typically you can purchase integrated modules, like you can see the diode of very low rating up to of 7 ampere IN 4001 we call it like, or you if you want like a rectifier module, that many diodes are already as a rectifier configuration. So, they are available in this form directly. It can be used from, you can connect directly the DC AC supply to it, and it at the output terminal it can give the DC. So, their size have reduced, their cost have reduced, and it is all the silicon solution which is quite efficient and having a low losses, very low losses. The efficiency has gone high, space requirement is also less, for these all rectification which use today in practice like, and there are of course have been further improvement of it. So, the diodes which are used for rectification, there are many type of diode, as you can see gun diode, LED diode, which use LED. Most of you might be knowing that today lighting system are based on LED, earlier we were using for signaling. Then pin diode, step recovery diode, laser diode, photodiode, tunnel diode, varactor diode, Schottky diode, and Zener diode. So, these are the typical symbol of them, and those were the physical, how they look like, and these are the like a typically simple junction diode, PN diode, then Zener diode, which have a characteristic similarity to block the voltage. We will discuss, of course, they use for in the clipper circuit, and then tunnel diode, Schottky diode, varactor diode. Then you have a diac light emitting diode, which already mentioned it, of course, with the arrow we saw, and photodiode, which are used of course for many, you can call it like a typically in counting or counters, just to, or even for estimation of the position, typically using such diode. So, they have a plenty of application in, of course, typically in case of your day to day life as a for the purpose of signal or rectification. And you can see how the rectifier module looks like of high power, which use the diode inside of it, and of course, the application of this rectification of is like a simple like a battery charger, because battery charger itself is get charged from AC supply, you rectified it, and then you can charge the battery, you can feed the DC current to the battery for the purpose of charging like, and I hope you are aware well, for the charger are used very extensively in large number of applications, these battery are used, so there we use the charger like. So, the simple concept of this, as you can say Zener diode, what purpose we use it, we have a single phase AC supply with the resistance, and then we have a Zener diode. So, you can just see how this typically, the output is here, that it clip the voltage more than diode Zener voltage, that voltage is clipped because it comes, the drop comes across the resistance, and then of course, in negative side, depending upon the silicon or germanium, if it is a silicon material used for this Zener diode goes to minus 0.7 volt. So, it goes to minus 7 to Vz, which where Vz is considered to be a breakdown voltage of the Zener diode, maybe like a 4.7 volt. They are available in different voltage, which are really made little safe. For 5 volt circuit we use 4.7, so that it give an inherent protection also. And you can just have again the back to back diode also for providing the clamping of the voltage. It does not go to the at the output. Many situations like we use in signal conditioning, other circuit for clamping. So, it goes plus minus Vz. On positive side, typically the lower one and upper one comes on negative side. So, you get very clipped output waveform from the this couple of the Zener diode. So, they are also used for the typically shaping the circuits or clipping the output voltage like also. And of course, we have a laboratory power supply that also give you the DC. So, it is also input is of course, the AC. So, we use the rectification there also, and or you have a inverter. So, inverter also of course, we feed the DC. So, for of course, feeding to inverter the DC, certainly we have a rectification. Then you have a light emitting diodes used for even for many purpose like a signaling, or you might have seen white LED for the purpose of lighting. Then of course, the LED are used for the displays like a 7 segment display, that number you can just have a display from typically 0 to 9, through these different segment display with the logical design. Of course, for the display of this you might have seen many typically display of such nature like also. Then your LED driver, which is used for the purpose of lighting system or many other driver, because the LED needs the voltage very low voltage. It is used hardly 3.5 volt, but you have a LED string for the purpose of lighting or for signaling or for display or for many purpose we use this LED string. So, there of course, we need the power supply, I mean, because you might be having many string, that is the reason they are made from, the output is from 36 volt to 72 volt as it is shown here, with the typically of 18 watt only. So, they are used typically for in generally lighting system. Then of course, the diode is used with this typically in this circuit for even a for filling purpose. If you have an inductive load, I mean, after this your chopper, I mean, it is conducting when you switch off, then certainly you must provide the variable path, so that the DC current is continuous and the load current is in spite the voltage may not be continuous, because you have to change the voltage by switching on of the choppers. So, we use the diode there also like. So, a lot of applications are there, or we use here wave shaping in clipper and clamper circuit. So, you can just see here we have input AC supply, we have a battery of some volt with the diode with resistance. So, here you will just see, I mean, with the BB, I mean, it will go to the typical, it will clip 0.7 to plus VB on this side, and negative side of course will pass through there. So, output will be of this shape. Similarly, here if you really add a capacitor which give kind of clamping, so whole voltage go to this on output side on positive side, I mean, negative portion get certainly goes out of it here, and you get the voltage from 0 to typically of 2 Vm because of this capacitor only and diode. So, this we call it like a clamper circuit, this we call it clipper circuit. We are clipping the waveform, here we are clamping the waveform on typically on both the sides. So, these of course, we like to discuss today this clipper as well as clamper circuit also like. Of course, these are the multi-pulse rectifier like 12 pulse rectifier. You can just see 3 phase we are converting to sets of 3 phase, and then we rectified it, and which give you us of course, better quality of the DC with less ripple in the output. Otherwise, you get the ripple in the output because of the AC rectification, because sine wave you are rectifying and output you are getting. And as you can see in the case of power supply, we have a reverse current protection, you have a DC supply and you have a load. So, well you feed it, so that the power should not go back to this. So, we connect the normally series diode. In many applications we connect it like maybe like a, you can see the solar panel or solar PV array, that we connect the diode, so that it does not feed back to the current to many such sources like common. So, that diode really are used in those applications also. This we are talking about typically for diode applications used in the DC circuit also. Now, coming to type of rectification, I mean, for conversion of AC to DC, there are plenty kind of rectifier. Basically, we have a here the two kind of rectifier, half wave rectify. As you can see here, you have AC supply and you are having a diode and then resistive load. So, it will you will see the waveform of this nature, which is only half cycle is available, another half cycle will be clipped because that is negative. So, diode will not conduct, diode will conduct only when AC supply is positive. So, you are just getting of this kind of half wave output on this the DC supply. But if you use the diode bridge rectifier, I mean, of this shape, you might have seen this kind of circuit in Wheatstone bridge. So, if we connect these 4 diodes in this manner, this gives the rectification. I mean, you will find if it is let us say positive, it will go through this load in this manner and it will return back to the AC source. And but if it is a or this is typically a positive, then it will go through this on the same terminal and it return back typically from this terminal to back to this. So, you just this diode rectifier provide the conversion from your AC to DC in both the half cycle, and you get the across this resistance all the time positive only. Of course, you will get a ripple voltage, but it will be always positive because of rectification provide the diode. So, we since it is a full wave, both the half wave are rectifying here. So, we call it full wave rectifier. Here it is only half wave is available. So, we call it half wave rectifier, but we use the here we use the one diode, here we use the typically 4 diode rectifier like. So, we can say half wave is the negative components of sine wave are discarded, and full wave the negative component are also inverted. So, while the output of rectification is now DC, current only flows in the one direction and output oscillate because of the, you can say it is really converted from AC supply. So, AC supply is really oscillating, that is the reason you will find ripple in the output, or you can some people call it like oscillation in the output. So, you can just see say input is a sine wave. If you have a half wave rectifier, you will get only positive half cycle in the output, but if you have a bridge, what we seen there, I mean, you will get a positive, but your negative is also inverted and you will get full wave in both the half cycle. So, the rectified output like, I mean, these are the two rectifier arrangement, I mean, typically used in practice like. So, coming to the rectification circuit is most popular application of diodes, and it converts alternating current to the direct current, and it involves the device that only allow one way of flow of electrons, and that is exactly what semiconductor diodes does. And simplest kind of rectifier circuit is the half wave rectifier consisting of one diode. As we discussed earlier, we have a typically input AC supply, which you can see on the waveform typically on the CRO and with the reading here, and then you have a diode rectification, one diode rectification which can only show the half wave in the output, even you have full wave at the input across the your typically across the load resistive load. So, you see this kind of waveform and we call it this as a half wave rectifier circuit. So, we have in a half wave rectifier the output waveform occurs only after each alternate half cycle of the input sinusoidal signal, and half wave rectifier generates an output waveform VO between the time period 0 t to t by 2. The polarity of the applied voltage is such that it makes the diode forward bias, and as a result the diode is turned on, and that is the forward voltage is more than the cut-in voltage of the diode, that is 0.7 for silicon, 0.7 volt for silicon, 0.3 volt for germanium. And this is the typically circuit you can just see. We have a diode, we have a input supply, we have a resistive load with the diode, and diode conduct only when positive half cycle is there. So, you get the waveform output of this nature like in this manner like typically, and you can just again explain that how it is the when it is a negative, then this circuit get open because diode does not conduct in negative direction and you get 0 voltage in the output during the negative half cycle in this typically for t by 2 t period of in the AC cycle like. So, this rectifier circuit for half wave, the process of obtaining unidirectional current and voltage from alternating current and voltage is termed as a rectification, and we use here the diode rectifier typically which have a PN junction here as you can see, and this is the typically simple, this we call anode, this we call cathode, and current flow from anode to cathode, and this is the typically you can say the characteristic of this diode rectifier or diode. This voltage typically is 0.3 for germanium, 0.7 for silicon, and this is the forward current typically with that voltage, and negative of course, you really have a small leakage current which is negligible, but you if you apply negative direction the very large voltage, this we call it Zener background or Alvanci background, then only it will have a large current, but that time it is susceptible to the very large heat or losses. So, device may damage. So, we never go to such large voltage, we keep a safe margin for the selecting the diode for a particular circuit or voltage applied to the circuit like So, the device that makes such a process possible is a diode. The ideal operating characteristic of which is given in this figure, which I already explained. When the applied voltage acts in the forward direction, there is no voltage drop across the diode and the current flows unimpeded. However, when the applied voltage acts in the reverse direction, a voltage drop appears across the diode and no current flows through it, and it is possible to obtain rectification by means of a single diode as indicated in the figure, and the current can only flow through the diode in one direction, and thus the load current can only flow during the alternate half cycle. So, for this reason the system is known as half wave rectification, and this is typically the half wave rectification circuit. You have a like a AC single phase AC supply with diode and with the resistive load, and you will just see this is the input voltage and this is the typically the current which is flowing into it. Negative half cycle current will be 0, and the output voltage and output current will be only positive voltage and positive current, and here you will have a 0 voltage and 0 current negative half cycle for this. So, we can say V is the instantaneous input voltage, supply voltage, instantaneous voltage across the diode, the VD, that is only typically 0.7 or it will be full voltage across it, and instantaneous voltage across the load resistance, that is this voltage, and instantaneous current through the diode, that is this current like So, that is, and using the of course, about the analysis using the Kirchhoff second law of closed circuit, we can say V equal to V D diode current plus the resistive load voltage, diode voltage plus resistive voltage, and that we can write the V D plus I R, or we can calculate from here the I equal to minus V D upon R plus V upon R, and where the supply voltage V equal to V m sin omega t, and we can say I equal to V upon R into V m sin omega t by R or I m sin omega t during the positive half cycle, considering that the diode drop voltage is very small compared to the V m like. So, from this we can find out even the DC current flowing through the load, that we can say positive half cycle. So, 1 upon 2 pi 0 to pi I m sin omega t d omega t minus I m upon 2 pi cos phi minus cos 0, that becomes I m, because that will be minus 1 with the minus, and this is minus already. So, it will become plus. So, it becomes I m, this will become 2 will cancel out. So, it become I m upon pi, and I RMS will be 1 upon 2 under root 1 upon 2 pi 0 to pi I m sin omega t square into d omega t, and keeping the value from this we get finally I m by 2, and we can say similarly the average voltage output will be V d c V m by 2 V m by pi, and V r m s will be V m upon by 2, that is for half wave rectify output. And we can calculate the efficiency of rectification. So, power in the load due to DC component and the total dissipated power in the circuit. So, this is I d c square r divided by I r m s square. So, this become I m upon pi square divided by I m by 2 square. So, this become 4 upon pi square, and which is nothing but equal to 0.405. So, mean value of the load voltage will be V d c upon V m upon pi for half cycle rectification, and R m s value across the voltage will be your V r m s equal to V m upon by 2. So, maximum voltage which occurs across the diode is reverse direction is known the peak inverse voltage. This must be less than the breakdown voltage of the diode if it is not to conduct appreciable in the reverse direction. Thus, the peak inverse voltage equals to approximately the peak value of the supply voltage. So, for most of the power application, half wave rectification is insufficient for task. So, harmonic content of rectifier output waveform is very large, and consequently the difficult to filter like. So, AC power source only supply the power to the load once only in a half cycle. So, meaning that the much of its capacity is unused, and half wave rectification is however very simple way to reduce the power to resistive load, and that is the reason it is used in such a dimmer circuit. So, 2 position lamp dimmer switches apply the full AC power to the lamp filament for full brightness, and then half wave to rectify it to the lesser output. So, you can just see the across this your filament the voltage get reduced it typically V m by 2 across the filament. So, that you can say this is for dim position because voltage is less, power is less, and for bright full voltage applies across the dimmer. So, half wave rectification is this application for 2 level lamp dimmer like. So, in the dim switch position, this incandescent lamp receives approximately 1/2 power it will normally receive operating on full wave AC. Because of half wave rectified, power pulses more than rapidly than the filament has time to heat and cool down, lamp does not blink. So, instead its filament merely operates at lesser temperature than normal, providing the less light output like. So, you can just have a dimming features in the lighting from this like. So, this principle of pulsing of power rapidly to slow responding load device to control electrical power and to is common in world of industrial electronics. And since controlling device diode in this case is either fully conducting or fully non-conducting at any given time, so it dissipate like little heat energy while controlling the load power, making this method of power control very energy efficient. So, this circuit is perhaps crudest possible method of pulsing power to a load, but it suffix as a proof of concept of application. So, if we need to rectify AC power to obtain full use of both half cycle of sine wave, the different rectifier circuit configuration must be used, and such circuit is called full wave rectifier. So, one kind of full wave rectifier is called center tape design and uses transformer with center tape secondary winding and 2 diodes, and this is the arrangement for we call it like a full wave rectifier with center tape design. So, the primary voltage say AC supply voltage is used primary across the primary of the transformer. This is also used to reduce the voltage level or to change the voltage level the transformer is used, and as well as the midpoint is for the rectification. So, we connect midpoint to the one terminal of the load of negative polarity, and both the diodes from both end of the winding we connect to the one terminal that called positive terminal across the load, and in one positive half cycle one diode another second half cycle another diode conduct, and you find the full wave rectification across this resistive load. So, that is the reason we call it your full wave rectifier. So, the transformer is used for the providing the midpoint. The benefit of this circuit that the drop of only of one diode is there and losses of one diode is there in the rectification. That is the benefit of this circuit. Of course, the transformer you have to use midpoint transformer, but of course, many circuit we have to change the level of voltage also from high voltage to low voltage. Like typically, you are charging the battery of 6 volt. So, certainly, from 220 volt AC supply you have to reduce the voltage low. So, transformer serve the purpose of isolation as well as to reducing the voltage, and then of course, it also facilitated because of midpoint the losses in the diode rectifier, because you are only one diode conducting at a time like of course. The disadvantage is you need the of course, the utilization of transformer circuit is poor in this case, because only one half winding is used at a time like. So, this circuit operation easily understood one cycle at a time, and consider the first half cycle when source voltage polarity is positive on the top and negative on the bottom. The only top diode is conducting and bottom diode is blocking the current, and the load sees first half cycle of the sine wave. Only top half the transformer secondary winding carries the current during this half cycle. As you can just see how it is there, the only top half, this typically the current is flowing typically in this manner in this load. So, full wave center tape transformer top half of the secondary winding conduct during the positive half cycle of the input and delivering the positive, typically you can call it the during the load. So, during next half cycle AC supply reverses, and now other diode and the other half of the transformer secondary winding carry current, while portion of circuit formally carrying current during last half cycle is sit idle, and the load still sees the half of the sine wave of the same polarity as before, and just now the lower diode conducted to provide the current, and you see another half. So, full wave center tape rectifier during negative half cycle, input half cycle, bottom of the secondary winding conduct and delivering a positive half cycle to the load. So, it reverted the polarity across the load, like this diode get connected with again with the positive polarity of the resistive load like. So, one disadvantage of this full wave rectification design is the necessity of transformer with center tape secondary winding, and if the circuit in question is one of the high power, the size and expenses of suitable transformer is significant, and consequently the center tape rectifier design is only seen in low power application. So, the basic full wave rectification network you can see here, primary one winding and secondary you have a two winding with the center tape, and how this rectification is there. So, here see the center tape on the secondary of the transformer, and thus the EMF induced in each section of the secondary are equal, and when the potential of A typically is positive with respect to C, so that the C positive with respect to the B. So, with these polarity diode D1 conducts while the D2 is in non conducting stage, and when these polarity reverse diode D2 conducts and D1 will be non conducting. So, in this way the diode conducts on alternate half cycles passing current through the load in the same direction. So, we can say VAC equal to V equal to Vm sin omega t, and VBC will be minus V and equal to minus Vm sin omega t. So, for this ideal identical diodes with a forward resistance R d equal to 0 and infinite reverse resistance, then the considering ideal diode, then the during the period that V is positive. So, diode D1 conduct and the ID1 will be Vm sin omega t by R, that is Im sin omega t, and diode T2 current is ID2 equal to 0, and during the period when Vs negative, then diode 1 current is ID1 equal to 0, and diode 2 current is ID2 minus Vm sin omega t by R, that is minus Im sin omega t. So, at any instant the load current is given by I equal to ID1 plus I22, and thus in this circuit the current will repeat itself twice every cycle of the supply voltage. Therefore, mean value of the load current is typically IDC equal to 1 upon pi 0 to pi, or you can say 2 upon 2 pi, or that is 1 upon pi 0 to pi Im sin omega t d omega t minus Im upon pi cos pi minus cos 0, and that becomes 2 Im upon pi or 0.637 Im, and IRMS will be again 2 upon 2 pi or 1 upon pi 0 to Im sin omega t square d omega t, and Im square upon pi 0 to 2 pi 1 minus cos 2 omega t by 2 into d omega t, and putting the value Im square by root 2 pi omega t minus sin 2 omega t by 2 0 to pi, that equal to under root Im square by 2 pi into pi, or Im by root 2 or 0.707 Im, and VDC is again similar way you can calculate 2 Vm by pi, and Vrms is V upon by root 2, and the rectifier efficiency is power in the load cell due to the DC component divided by total power dissipated in the circuit. So, IDC square by R, IRMS square by R. So, that is 2 Im by pi square, Im by root 2 square. So, it becomes 8 upon pi square and equal to 0.81. So, now the waveform for the full rectification circuit you can see here, the voltage is positive half cycle out of this, and current is also all the time positive ID1, I2, ID2 and I. So, load current will be here ID1, here ID2, diode 1, diode 2 go on conducting in consecutive half cycles like. So, another more popular full wave rectifier design exists and it is built around the 4 diode bridge configuration for obtaining this design called full wave bridge rectifier. This is full wave rectifier. So, you have a AC supply input and now you have a 4 diodes and you have a resistive load and you have a same rectification full wave rectification here, and the process which I will already explain that when it is a positive it conduct this way, this connect to positive and then return back and it goes to back to this way. When this is negative it goes typically, or this positive it goes in this manner, it comes through the load and goes this way to this supply. So, in this process you will find typically the rectifying both way half cycle, the diode rectifier is virtually to convert from AC to finally to unidirectional voltage output across the load, and that you get a full rectification in this manner. Here you can consider that you are not using the transformer, that is the benefit, and but the limitations is you are not providing the isolation as well as you can't change the voltage level, whatever voltage you are getting from input you get rectified in the output. So, current direction for full wave bridge rectifier circuit for positive and negative half cycle of AC waveform is shown, and note that the regardless of the polarity of input current flows into the same direction through load, and that is the negative half cycle of source is positive half cycle at the load, and full wave bridge rectifier electron flows from positive half cycle and then full wave electron flows from negative to half cycle, and the efficiency of the now the network is eta equal to IDC square by RMS square and 2 IM upon pi square divided by IM under root 2 square. So, that becomes again 8 by pi square equal to 0.81. So, neglecting the forward resistance of the diode, the voltage appear across the non-conducting diode is equal to the supply voltage. Thus, the peak inverse voltage is equal to the peak value of the supply voltage. So, there are certain advantages to be obtained by using the diode bridge circuit as opposed to the center tape circuit, secondary full wave circuit, and for a given mean load voltage or average load voltage, the bridge rectifier uses only half of the number of secondary turns, and for the diode of given maximum peak inverse voltage rating, twice the mean output voltage can be obtained from it, since the peak inverse voltage encountered is Vm compared to the 2 Vm for the full wave circuit. Now, current flow is through the 2 diodes in series for both polarity, thus the 2 diode drops of source voltage are lost 0.2 into 2, that is 1.4 volt for silicon diode, and this is the disadvantage compared to the full wave center tape design, and this is my only problem in very low voltage power supply. In case of rectification, amount of AC voltage mixed with the rectifier DC output is called ripple voltage, and in most of the cases since pure DC is desired goal, so ripple voltage is undesirable. So, if the power level are not too great, filtering network may be used employed to reduce the amount of ripple in the output voltage. So, sometime method of rectification is referred by counting number of DC pulses output for every 360 degree of electrical rotation, and single phase half wave rectifier circuit then would be called one pulse rectifier, because it produces single pulse during the one complete cycle of 360 degree of AC waveform, and since full wave rectifier regardless of design center tape or bridge would cause 2 pulse rectifier, because it output 2 pulses of DC during the 1/2 cycle of the worth of time, and this is you can call it like a simple same diode rectifier, full wave rectifier, and of course, we are using here the capacitor for the purpose of filtering, typically getting a better DC across the load, and this can be equated here with the rectified DC here of this nature, this is this nature, and in series with the diode, and this diode will conduct only when you can call it this voltage more than the capacitor voltage, and of course, the load current will be continuous because capacitor will give the voltage. So, you will get some ripple, and the ripple will depend on the time constant of the circuit, this RC circuit, otherwise this will give a good quality DC at the output, and you can just see what the output voltage of the DC, when it is really getting discharge here, once it the supply voltage goes more than the your capacitor voltage, you get increase the supply get connected and you get the positive, but after that in negative half cycle again this capacitor get discharged across the load. So, like that you have output voltage with a certain some ripple, but of course, ripple get reduced, it is not touching the 0 and it is not going to be very high voltage. The average value of the output load voltage VDC and the average value of output load current IDC, the output DC power is equal to PDC equal to VDC into IDC, and that IDC because of load we can consider very small ripple in the load current line. So, the root mean square value of the output voltage VRMS the RMS value of output current, and then we can call it the output AC power is your VAC equal to Vrms I RMS, and effective mean value of AC component of the output voltage is VAC under root Vrms square minus VDC square, and the ripple factor, which is a measure of the ripple content, is defined RF equal to ripple filter equal to VAC upon VDC under root Vrms square divided by VDC square minus 1. And you will just see this kind of waveform we are applying. I mean, as you can see here the dotted line, and what kind of output voltage across the load we are getting. Typically here in this duration, when your supply voltage is becoming more than the capacitor voltage, it getting charged, and after that it get discharged for reasonably long time, depends on capacitor value and resistance one. So, this kind of voltage waveform across the load you will get from this circuit like, and the ripple voltage from this, if you can see, I mean from the average voltage, if you see the ripple voltage, here it is the over average voltage, this will be the ripple voltage, I mean, or plus minus corresponding to in across the in the output. So, when the instantaneous supply voltage is higher than the instantaneous capacitor voltage, that is the capacitor C is then charged from the supply, and if the instantaneous voltage V s falls below the instantaneous capacitor voltage, then the capacitor C discharges through the load resistance, or you can say diode does not conduct during that. So, whatever energy is the capacitor across the capacitor, it goes to the load, and this is typically how you are getting typically with the, I mean, two diodes in series for the bridge, I mean, which is going across the capacitor, and this capacitor of course, when discharging, I mean, when the voltage is supply voltage lower than the capacitor voltage, then only capacitor discharges across the load. And this is the same what we talk about, that okay, capacitor charges only when it the capacitor supply voltage more than the capacitor voltage is charges, after that is discharges, again charges in another half cycle, and that, and this is the ripple voltage. So, capacitor voltage VO varies between minimum voltage and maximum voltage, and the output voltage ripple is then the difference between the maximum voltage VO max and the minimum voltage VO minimum. And let us assume that Tc is the time period, I mean, you can say here for diode conducting, and then Td is the time for discharging. So, discharging time is typically this much and charging time is this much. Charging time is very small and discharging time is quite large in this circuit, as you can see from the ripple waveform also. So, during the charging interval, the capacitor charges from VO minimum to Vm to peak value of the voltage. So, let us assume that an angle alpha, the positive going input voltage is equal to the minimum capacitor voltage at the end of the capacitor discharge, and at the input rises sinusoidally from 0 to Vm, the angle can be find out VO equal to Vm sin alpha, or alpha can be sin inverse VO minimum divided by Vm, and during discharge current from the capacitor discharges exponentially through the load resistance. So, we can say during discharging mode, you can write a equation on, I mean, the voltage across capacitor C 1 upon C integration of I dt, that is the voltage across capacitor, minus V c at the time equal to 0, that is the initial condition, plus I 0 R L, and from with the initial condition V c 0, this is Vm. So, we can say I 0 equal to Vm upon R into e to power minus t upon R L into C for the period of 0 to t go to T d. So, instantaneous output voltage or capacitor voltage VO during the discharging period can be written as VO equal to R L into I 0, that will Vm e to power minus t upon R L into C, the time constant like. And from this waveform you can see what is the beta and what is typically the period, like a whole period. So, we can say the discharge period T d or the discharging angle beta can be written as omega t d equal to beta, that is pi by 2 plus alpha, or at t equal to T d the VO becomes equal to Vm, VO minimum, and then we can replace T d to VO minimum by. So, VO at t equal to T d, that is VO minimum equal to Vm e to power minus T d upon R c into C. So, hence the discharge period, from that equation we can calculate the T d equal to R L into C ln Vm upon VO 0 minimum, and equating T d from this equation to this, we can get omega R L e ln Vm upon VO minimum equal to pi by 2 plus alpha, or it is equal to pi by 2 plus sin inverse VO minimum upon Vm, and therefore, the filter capacitor can be find out CO equal to pi by 2 plus sin inverse VO minimum divided by Vm divided by omega R L ln Vm upon VO minimum. And referring to the time period omega t equal to 0 at pi by 2, when the discharging interval begins, we can find out the average output voltage. So, V average is Vm upon pi in bracket 0 to beta e to power minus omega t upon r l into d omega t, and beta to pi, that is cos omega t d omega t, and we can solve it. So, it comes V m upon pi in bracket omega r l c in bracket 1 minus e to power minus beta upon omega r l c plus sin beta, and these equations for C, we can solve C for V average are non-linear. So, we can derive the simplest explicit expression for ripple voltage in terms of capacitor value if we make the following assumption. So, assumption, if we assume that the charging period is small compared to discharging period T d, then or you can say T d is much larger than T c. So, which is generally the case. So, we can relate T c and T d to be period T of the supply. So, we can say T d is almost T d by 2 minus T, or which is almost equal to T d by 2 or equal to 1 upon 2 f, corresponding to that related to supply frequency or input frequency, and using a Taylor series expansion of e to power minus x equal to 1 minus x with the approximation for a small value of less than 1, then this equation can be simplified equal to V o minimum equal to V m e to power minus T d upon R L e equal to V m 1 minus T d upon R L into C, and the peak to peak ripple voltage V r can be written here V r equal to V m minus V o minimum or equal to V m T d upon R L C e equal to V m upon 2 f R L C e. So, this equation can be used for to find out the value of capacitor with a reasonable accuracy for most practical purpose as long as ripple factor is within 10%, and we can observe that this equation that the ripple voltage depends on inversely supply frequency, the filter capacitance and the load resistance. So, if we assume that the output voltage decreases linearly from V o to V maximum to V minimum during the discharging interval. So, the average output voltage can be written found approximately equal to V o equal to V m upon V o minimum by 2 or half in bracket V m plus V m 1 minus T d upon R L C e, which after substituting T d becomes V o half V m plus V m 1 minus 1 upon R L 2 F c or V m 2 minus 1 upon R L 2 F c e. So, we can say ripple factor can be found out R f equal to V r peak to peak by 2 divided by V o average, or it becomes 1 upon 4 R L F c minus 1. So, the peak input voltage V m is generally fixed by the supply, where the minimum voltage V o minimum can be varied from almost from 0 to V m by varying the value of C, F and R L. So, therefore, it is possible to design average output voltage in the range of V m by 2 V m, and for eventually expression for ripple factor output average voltage and the filter capacitor can be obtained. V average equal to V m by 2 in bracket 2 minus 1 upon 2 R L F C e, or C equal to 1 upon 4 F r in bracket 1 plus 1 upon R f. You can find out capacitance for given ripple factor and load resistance and frequency of supply, or ripple factor can be 1 upon 4 R L F C minus 1. So, coming to a numerical example based on that, a single phase bridge rectifier is supplied from 120 volt DC 60 hertz source. The load resistance is R equal to 500 ohm, and design a capacitor so that the ripple factor of the output voltage is less than 5% with the value of capacitor C part A, and calculate the average voltage. So, here ripple factor is given 5%, that is 0.05, and V m equal to 120 root 2, that is 169.7, that is around 169. So, C is 1 upon 4 F r in bracket 1 upon 1 by R f equal to 1 upon 4 into 60 into 500 bracket 1 plus 1 upon 0.5, that becomes 175 microfarad, and the average DC voltage V equal to V m upon V m by 2 in bracket 2 minus 1 upon R L 2 F C e equal to 169 by 2 in bracket 2 minus 1 upon 502 into 60 into C, that is 161 volt. So, that is now 3 phase rectifier what we use. We have again transformer primary, let us say delta and secondary star, and we have a 3 phase diode rectifier to rectify 3 phase supply to get the DC. Of course, in 3 phase we get the better DC because you get the 6 ripple across the output. So, ripple voltage reduces in this 3 phase rectifier, and how the waveform are there. These are the input voltage, this is the typically the kind of rectified voltage, and this is the supply current. So, it conducts for 120 degree, and this is the diode current how to rectify in 3 phase bridge rectifier. So, now coming to this rectifier review circuit, we say rectification is a conversion of alternating current to direct current, And coming to first as a half wave rectifier, a half wave rectifier is a circuit that allow only one half cycle of the AC voltage waveform to be applied to the load, resulting in one alternating polarity across it. And full wave rectifier is the circuit that contains both half cycle of AC voltage waveform to unbroken series of voltage pulses of same polarity, and 2 is the resulting DC delivered to the your load pulsates significantly. So, resulting DC delivered to load does not pulsate as much. So, now coming to the rectifier circuit application. This rectification circuit applications are DC supply used to provide the DC power to drive the loads, and typically used in radio to rectify received radio signal as part of the AM modulation, and signal to be transmitted and multiplied by a carrier wave and diode in receiver rectified signal. As you can see the example, we have a audio signal, we have a modulated signal, and then we have a radio transmission, and this is typically that the signal after rectification of the diode we get the signal only for rectified radio wave. The other application is typically the light dimmer, send the uncorrected or half wave AC supplied across the, when you want bright, the full voltage applied across the lamp, and when you bring down through diode is only the reduced voltage or the is applied across the load. So, you get the dimming effect across the this bulb like. Another is automobile alternators, output of 3-phase generator is rectified by diode bridge. As you can see it, because earlier we were using the dynamo in most of the, typically you can call it automobile, but now we are using AC generator which are brushless generator most of the time with the permanent excitation. So, you get the more life, no maintenance, and the maintenance requirement. So, but we have to rectify this variable AC voltage which we are getting from 3-phase alternator permanent generator. So, for that we use again the 6 diode rectifier for this purpose and provide the more reliable than the DC generator. Now, coming to the typically the other topic of clipper and clamper circuit. So, a clipper is the type of diode network that has the ability to clip off a portion of the input signal without distorting the remaining part of the alternating waveform, and half wave rectifier is an example of the simplest form of the diode clipper, and one resistor and one diode, and depending upon the orientation of diode, the positive or negative region of the input signal is clipped off. So, as you can see here, there are 2 general category of clippers, series and parallel. So, series clipper, a series clipper and its response for the 2 types of alternating waveform are shown. So, if you are applying the square wave here with the diode, out of this square wave only positive half cycle remains there, but if you apply the triangular wave here, you only positive half of triangular wave is applied. Even if you apply sine wave, you will get only positive half cycle of the sine wave, this series clipper circuit like. So, the key points here, the first step to find out the in which interval of the input signal the diode is forward bias, and the direction of the diode suggests that the signal Vi must be positive to turn on it on, and DC supply further requires the voltage Vi to be greater than V volt to turn on the diode on, and the negative region of the input signal turns the diode into off condition or on off state. Therefore, in the negative region the diode is an open circuit. As you can see typically here with the we have a series clipper with the DC supply. So, we have a input supply here with the DC source, and this also typically provide the kind of varying voltage across the resistance. So, here the determine the applied voltage, transition voltage, that will cause the change in the state of diode. So, for ideal diode, the transition between the state will occur at the point when characteristic Vd equal to 0 and Id equal to 0, and applying this condition it recognize that the level of Vi that will now cause a transition is equal to V equal to Vi, as we have seen the charge capacitor there. So, for the input voltage greater than V volt, the diode is in the short circuit state, while the input voltage less than V volt, it is open circuit in off state. So, this capacitor this voltage DC voltage will only allow to conduct when this AC applies more than the this voltage, and then only this diode will conduct. And of course, in case of reverse way also, this will put the V in the VO in the clipper circuit for the purpose of this conduction of positive half cycle. So, you can just see here, being continuously aware of the defined terminal and polarity of VO, when the diode is in the short circuit state, the output voltage VO can be determined by the applying KVL in the clockwise direction. So, VO will be equal to Vi minus VO, here typically only in this region where this is more than that, and it goes to typically up to minus V. So, it can be helpful to sketch the input signal above the output and determine the output at instantaneous value of the input, and it is then possible to sketch the output voltage from the resulting data points of V o. So, for V m greater than V, the diode is in the short circuit state and V o equal to V m minus V, and at V i equal to V, the diode changes state from V i equal to minus V m and V o equal to 0 volt, and the complete curve for V o can be sketched. And you can just see here, the diode which is in series. So, it's only changes the voltage typically, start from here, it will start conducting only at the voltage of V, and it goes only from this much portion comes as a clip at the output like. So, it start conducting only your this supply voltage is equal to V, it start conducting here and stop conducting when it equal to minus V, and so only that much portion is in the output here. So, you are just clipping only portion of the positive half cycle also, not the whole positive half cycle is across the output across the resistive load in this circuit. So, that means kind of clipping we are providing only portion of half cycle only, not the full cycle like. So, there is another circuit called parallel clipper. The input voltage V is applied to the output V o, and the analysis of parallel configuration is very similar to the series configuration. So, here we have input supply, we have a resistance and we have a diode here, and this output is will be there when the typically diode is not conducting like. So, this will be the you can say input wave, if it is a square wave, the output will be only negative half cycle, because during that this diode will not conduct, positive half cycle diode will conduct. So, you will have a 0 voltage in the output because of only small drop of diode conduction. Similarly, in this response of parallel clipper will be that the negative half cycle only will appear across the output across the diode, because it will not conduct, it will be reverse bias, but positive will not diode will conduct during that period. So, there is a discontinuity at the voltage V y. So, actually the transition of a diode state is not exactly abrupt, but gradual. So, thus a waveform which is transmitted through the clipper circuit will not show an abrupt clipping, instead it will show the gradual broken region exhibiting the regions of unattenuated and attenuated transmission. And now, we will estimate the range of this break region. The output current of the diode is given by equal to I 0 e to E V upon N into V t, and you can say the increment diode resistance is R equal to d V upon d I is the given by R equal to N V t upon I 0 e to power minus V upon N V t, or it can be approximated equal to N V t upon I. So, again for meaningful clipping to be done, the applied signal must vary from one side of the break point to the break well on the other side. And here you can just see the simple series clipper, as we already discussed that here only diode will conduct only typically on the negative half cycle. So, negative will appear, and if you have supply voltage here this of opposite, so it will conduct even from typically 0 to minus V m. This will also add into it. So, you will get 0 to minus V m, and if you have a typically here it will minus V m to minus V, that will appear across the output like. And for negative again here for negative clipper, this will be only positive half cycle, and if you put a voltage across this, that will be from not minus V m, it will be going to be minus from that term, it will be only V m minus 0 to V a to V m minus. So, it is only you can say the waveform is cut even from the minus V. Similarly, here also the waveform, when you put the change of polarity of here, you will get 0 to V m plus V. So, how this adding a voltage along with the diodes, going to change the waveform of clipping from either to let us say V m to plus V or V m minus V, positive of negative half cycle, that are shown here like typically. So, these are different of course, various circuit associated waveform of clipper circuit, and these are some more additional waveform than when that is for series, that is for here the parallel clipper. So, you will get only negative half cycle. When you put series voltage here, you will be clipping from minus V to minus V m, and here if you keep series with the typically here, you will get the most of with the opposite polarity. So, you will get minus V m, but only add input voltage will add only for the portion of when it will be greater than minus V, and you can have a both in with the batteries plus minus. So, you will get clipping on V 1 and V 2 and positive and negative half cycle, and similarly you can have here only typically again positive half cycle if diode is of this way you are keeping. So, output will be when the diode is not conducting, that is only positive half cycle. Here it will be clipped from negative minus V to V m, and this will conduct again from 0 to V will not be, only additional will come only V m. So, this voltage will be virtually going from 0 to V m, but with the other portion also will be V will appear across the load when that typically you can call it supply is not connected to it like. So, now another circuit R we call it clamper, which clamp the waveform. So, here you can see the, let us say we have a AC wave or square wave at the input, and we have a capacitor here and diode also along with the resistor. Though obviously, the output here the clamping network is that will clamp a signal to a different DC level, and the network must have a capacitor, a diode and a resistance element, but it can also employ an independent DC source to introduce an additional shift like. So, before further probing into the clamping circuit, one must have a basic understanding of the tangent RC circuit, and from the basic understanding of a series RC tangent circuit applied across the DC voltage E 0, the instantaneous charge across the capacitor at any time is given by, typically here we know that the time constant of t equal to RC of this circuit. So, right time becomes a smaller if we decrease the time constant, or we say R or time constant reducing means we have either a low capacitor or low resistance. Here q equal to q 0 1 to power minus e to power minus t upon RC, and how this capacitor is getting charged with respect to the time constant. We presume that at 5 time constant it will be typically going to be fully charged like. So, the discharge will occur quickly if the time constant of the circuit is decreased. So, the magnitude of R and C must be so chosen that the time constant t equal to R C is large enough to ensure that the voltage across the capacitor does not discharge significantly during the interval the diode is conducting, and q 0 equal to E 0, q 0 equal to E into C, where C is the capacitance of the capacitor. And you can just see how it is a discharging of this RC circuit from q charge capacitor to up to 5 time constant, it will be completely supposed to be discharged to almost 0 value. So, now using this concept we have a clamping circuit, because here circuit will be coming in RC circuit in this waveform. So, you have typically here at the you can call it the circuit during diode on period, you will get the output, and circuit during the diode off period when diode is not conducting, that will get open circuited. So, what the input and output wave, input waveform is your square wave, and the output will be your only your negative wave, because that voltage get added of the V, because both are V. So, it will get from 0 to minus 2 V, because of the diode conduction during this period and non diode conduction during that period. So, during the interval 0 to t by 2, the network will appear with the diode in on state effectively showing out the effect of resistance, and the resulting RC time constant is so small that capacitor will discharge to V volt very quickly, and during this interval the output voltage directly across the source circuit at V equal to 0 volt, and diode will now be in the open state condition. So, applying KVL around the input loop of the figure will result in V equal to minus 2 V, and the negative sign result from the fact that the polarity of the 2 V is opposite to the polarity of the define of for VO, and for the clamping network the total swing of the output is equal to the total swing of the input, and that is VO equal to minus 2 V, and this is typically various clamping circuit and associated waveform. So, we have a square wave with the typically the again capacitor here with the diode. So, considering that the here you can call it the capacitor voltage will be also added, and diode will not conduct in negative half cycle, it will conduct only in positive half cycle. So, you will get a 0 to 2 V only when typically you have a you can call it the your negative half cycle, diode will not conduct, positive half cycle the capacitor will get charged for V and output voltage will be 0, but capacitor will get charged for negative half, the capacitor will not get because diode will not conduct, capacitor will not discharge. So, voltage across this will be a capacitor voltage and input voltage will appear across the output, and here also you will get of course, this supply voltage will get added, that will appear for the positive half cycle, remaining will be 2 V will be there. Similarly, here you will get up to V 1, it will be with the negative polarity, it will be 0 to minus V 1 during the period when diode is will typically appearing and conduct, and then remaining period it will be sum of the 2 V plus V 1 minus So, entire all V 1 minus. Similarly, here when diode polarity changes, you will get all these in positive side. I mean diode will conduct, I mean to typically to charge the capacitor in that polarity, and output will be 0, and during other period when diode does not conduct, you will get 0 to 2 V, because of capacitor will also charge with the V. And similarly, here of course, you will add this voltage also from 0 to V 1, then 2 V, and then here you will have a this on minus side, the minus V 1. And then if you apply sine wave with this and with this 10 volt, you will find the waveform will be shifted from minus 10, you will get output because of this will be there here. I mean this will conduct and will come output, and you will get up to typically the voltage added, this 10 volt with the 20 will added with the output. So, you will get a kind of sine wave with the offset of 10 volt added into it also. Now, coming to the some of the numerical problems related to this, a full wave center tape rectifier circuit is shown here, and assuming that for each diode the cut in voltage is 0.6 volt and the diode forward resistance is 15 ohm, the load resistance R equal to 95 ohm, determine the peak output voltage across the load and sketch the output waveform VO. So, it is like a your full wave rectifier with center tape, and we can say the peak output voltage V s equal to 125 by 5, that is 5 volt, and that V tangent plus I D into 15 plus I D 95 minus equal to 0. So, from this we can find out what is this typically, or you can call it I D equal to 5 minus 0.6 volt divided by 110, that is 0.04 volt, and V O equal to peak equal to 95 into 0.04 3.8 volt, and you will get this kind of the waveform of 3.8 volt in the output maximum, and will be of this kind of waveform in this circuit like. So, coming to the numerical problem second, determine the currents and voltage of the half wave rectifier circuit. Consider the half wave rectifier shown in figure, assuming V b equal to 6 volt, R equal to 120 ohm, and V gamma equal to 0.6 volt. Also assume that V s equal to 18.6 sin omega t. Determine the peak diode current, the fraction of the wave cycle over the which the diode is conducting. So, peak diode current will be I d peak equal to V s peak minus V gamma minus V beta upon R, and that will be 18.6 minus 0.6 minus 6 by 120, that is 100 milliampere. And typically a simple circuit, how it is really going to be the battery charger, I mean through rectifier, I mean that is a simple circuit of that. And now diode conduction is started at the here V 1 equal to 18.6 omega t, that is V gamma plus V b, that is 0.6 into 0.6 6.6 volt, that is start conducting, and theta will be corresponding to that. We can find out of sine wave, this become 20.78 where the diode is start conducting, and theta 2 where the diode ceases conduction, that will be 180 minus same angle 20.78 degree, that is 159.217. So, this 159 minus 20.78 during this period only this diode will conduct like. So, the percentage of conduction with the respect to full cycle will be theta 2 minus theta 1 by 380 into 100. So, you can keep the value and it comes around 38.453% like. And now numerical 3, sketch the output voltage V o and determine the DC level for output network of this figure. So, repeat this for ideal diode is replaced by a silicon diode. So, you have a sine wave of plus minus 20 volt and we are keeping diode. So, this diode will conduct only, you can call it only your negative half cycle, positive half cycle it will block like. So, you will get a only negative part of it here. So, in this situation the diode will conduct during the negative part of the input cycle, and V o will appear as shown in the figure. You can see the voltage here, that will be equal to V d c equal to 0.318 into V m or equal to minus 0.318 into 20. So, that voltage will be 6. DC average voltage will be 6.36 volt, and negative sign indicate that the polarity of the output is opposite to that of define of typically of this figure. And for the silicon diode, the output appear across this, we have to take a drop of silicon diode virtually. So, 0.318 V m minus 0.7, and that we calculate 6.14, because it is a low voltage, that is why the diode drop of 0.7 volt also affected, and resulting drop of DC will be now by 2 volt or about 3.5% in such voltage, because 19 volt 20 volt itself is a quite low volt compared to. Now, coming to numerical 4, determine the output waveform for network here and calculate the output DC voltage for this typically for this segment. So, when you apply this, you will find the voltage across typically output of this nature, as you can see in positive half cycle it conducts and negative other diode will conduct. And so, we can say solution. the network appears as in for the positive region, and redrawing this network we say V o equal to half V I or V o max equal to half V I max equal to half 10 volt or equal to 5 volt as shown in, and for the negative part of the input the role of diodes are interchange and V o appears as shown in 4D. So, you can just see what the network is there with the voltage applied here, like, and then you get the second half also for resulting output. So, the effect of remaining two diodes from the configuration is therefore to reduce the available DC voltage VDC equal to 0.636 into 5 3.18 or available half wave rectifier with the same input. And now determine for this triangular wave with 16 volt amplitude applied to input and with this 4 volt with series diode. And so, in this wave, in this example the output is defined a series combination of 4 volt supply with the diode and across the resistance. So, second step, the polarity of the DC supply and the direction of diode strongly suggests that diode will be on during the good portion of the negative region of the input signal. In fact, it is interesting to note that since the output is directly across the series combination, when the diode is in short circuit state, the output voltage will be directly across the 4 volt DC supply, requiring the output to be fixed 4 volt. In other words, when the diode is in, output will be 4, the other way state the diode is in open circuit and the current through series network will be 0 milliampere and the voltage across the resistor will be 0. That is the result V o equal to V I whenever the diode is off. So, the transition level of the input voltage can be found from this figure, substituting the short circuit equivalent and remembering the diode is 0 milliampere at the instant of transition and V I will be typically of 4 volt. And now, typically the transition level of V o equal to 4 volt when diode is on, and then the waveform will be V o equal to 4 and the waveform is simply shown typically here in this plot. And now, determine the network of shown figure here. This is the typically input waveform to calculate output waveform. So, it varies from -20 to +20 with 1000 hertz. So, note the frequency of 1000 resulting in a period of 1 millisecond and interval of 0.5 second between the two levels. So, analysis begins with the T1 to T2 of the input signal. Since diode is in short circuit state, for this interval network will appear as shown in the figure 1b. The output is across R, but it is also directly the 5 volt battery and one follows the direct connection between the defined terminals of the V o and battery. So, result is P o equal to 5 volt for this interval. Applying Kirchhoff's voltage law, you can say -20 volt plus V c minus 5 equal to 0. So, V c will come 25 volt and you will find this here the voltage like this diode will conduct when your 20 it is more than 20 volt. So, across the resistance you will get typically added the voltage. So, the capacitor will therefore charge up to 25 volt. In this case the resistance is not sorted by the diode. So, but the Thevenin equivalent the portion network that includes the battery and resistor will result R T h equal to 0 and it is equal to 5 volt, and for a T 2 T 3 the network will appear as shown in, and the open circuit for the diode remove the 5 volt battery from the having the effect of V o and applying the Kirchhoff's voltage law around this. So, minus 10 volt plus 10 volt minus plus 25 equal to V o, V o will be now 35 volt, and that is the typical circuit that you will have a voltage how it in the circuit will be there. So, the time constant for the network is determined by the product of R c. So, T equal to R c 100 kilo ohm into 0.1 microfarad, that is a 0.01 second. So, 10 millisecond. So, total discharge time is therefore 5 into T, that is 5 into 10, that is 50 millisecond. So, since the interval T 2 to T 2 to 3 will only for 0.5 millisecond. So, it is certainly good approximation that capacitor will hold its voltage during the discharge period between the pulses of the input signal, and resulting output from you can just see in here in typically 1D. This will be the output voltage coming across the output terminal or so from the input. So, these are the references from where we have taken developed this lecture, and thank you very much.